Welcome to our lesson on electrostatic force. Now, electrostatic force is one of the fundamental forces of the universe, and it governs various different things that we see all around us. For example, everything from lightning storms, which are as a result of static electricity and charge buildup and then discharging, to the bouncing up and down of a basketball and might be used as a way to explain why the basketball doesn't fall through the floor, to our very small little atoms, of which there are billions that make up the screen that you're looking at. So we have some degree of familiarity with electrostatic force already, and we know that certainly in the atoms, the atoms are contained of have particles within them rather, and those particles and those charges are governed by something called the law of electric charges, and that states quite simply that like charges repel and opposite charges attract. So the two red charges, which are positive in this case, will repel or push each other apart, and the positive and negative charge, which are opposite charges, would repel, and that's something that hopefully we're all familiar with. If we look at that in the context of an atom, it's what keeps the electron orbiting in various different parts of the atom. It keeps it orbiting around the nucleus. It's also what causes the atom to break down when we talk about bigger elements, because those positive protons in the nucleus eventually, when their distance between them gets very large, those blue gluey neutrons cannot quite hold them from busting apart. But that's a conversation for another day, I guess. So the question is, we know that these charges have a force between them, and we know that they can attract or repel. But what factors affect the force between subatomic particles? Well, that's a question that boggled the mind of one Charles Coulomb, a French physicist. He was very interested in charges and did a lot of experiments to find how charges behaved in connection to one another. And he came up with a law or an equation which is now known as Coulomb's law. And it states simply that the electrostatic force between two charges would be equal to K Q1 Q2 over R squared, where K is a constant, a proportionality constant, which he worked diligently to find. And Q1 and Q2 are what we use to represent the charges, and R being the distance between. So if we look at that and just dissect it a little bit, it means that the electrostatic force is proportional to the charges themselves, the magnitude of the charges, and is inversely proportional to the square of the distance between them. Well, does this equation for electrostatic force remind you of another force equation by any chance? Well, if you said that it reminded you of gravitational force equation, your Fg is equal to gm1m2 over r squared, then you'd be correct. It is quite similar to the electrostatic force equation. And in physics, this inversely proportional to the distance between them, the inverse exponential proportionality comes up quite a bit. So let's see what are the similarities and differences between these two different forces, two of the four fundamental forces in the universe. Well, firstly, Fg, the gravitational force, of course, is proportional to the masses. It's always attractive, and it's much smaller than electrostatic force. The electrostatic force is proportional to charges. It can be attractive or repulsive. It's a force that can actually push away. It's not necessarily attractive force. unlike the gravitational force. And it is much larger than the gravitational force. If you want to, maybe have a think about that, why would it make sense that the electrostatic force is much larger than the gravitational force? Well, maybe think about that basketball dropping to the ground and dropping to the floor, and maybe ask yourself why that basketball doesn't go through the floor. So two different forces are at play there. One is clearly stronger than the other. What do these these forces have in common? Well, they're both inversely proportional to the distance between the particles and the objects. They both involve a proportionality constant, although we've talked about how the one for electrostatics and Coulomb is larger. They both were discovered using or fine-tuned using torsion balances. And that, if you want to find out more about what the torsion balance is, I suggest you look at perhaps another video. There's lots of really good videos out there as to experimentally how these were found. And they're also two of the four fundamental forces of the universe. So Coulomb's law. We've talked about how it is K Q1 Q2 over R squared. K being a proportionality constant value, and you can see here it's 9.0 by 10 to the 9, so a very, very large number. There's two things to bear in mind when we talk about Coulomb's law. Number one, the direction of force lies on the line joining the center of charges. And number two, when a charge experiences force from more than one charge, direction must be resolved also. So this is very, very important to note, because when you have more than two charges, you will have to solve the force for acting upon that charge by each of the individual charges. And very often what that's going to give you actually is the makings of a 2D problem, because you'll have to add those forces together, and force being vectors, if they're not all along the same line, well, then we've got a 2D problem. Okay, so let's look at a simpler example. Two charges of magnitude 1.6 by 10 to the negative 17 coulombs. The magnitude of charge is measured in coulombs. Think of Coulomb like a bucket of charge. It represents a huge amount of charge, similar to Avogadro's constant, 1 mole, if you're familiar with that term in chemistry. It is an enormous bucket of charge. So it is very common for charges to have a very small magnitude in terms of Coulomb. And so two charges of magnitude 1.6 by 10 to the negative 17 coulombs are separated by a distance of 180 nanometers. So very often we underline these important things we're given. What is the size of the electrostatic force experienced by each charge? Okay, so it's not the total, it's by each charge. Well, good physics principles, good physics folk will do the following. They will underline their givens. They may draw out a pictorial representation. We can see the two charges. It's important to note that they're both positive, so there will be repulsion here. The charges are the same size, so we will represent that showing the circles of the same size or magnitude. And we're going to write out our givens. You might want to, right now, it would be a good idea maybe to write that 180 nanometers in terms of units that we are more familiar with, the standard SI units, the units that we know and love. 180 by 10 to the negative 9 meters. And what we're looking for is FE, of course. So FE is equal to K times Q1, Q times Q1, Q2, which is Q squared in this case, because they're the same magnitude, all over the distance between them squared. Now at this point, I might like to recommend that you get familiar with doing these, because what you'll notice is that there's a lot of exponents, a lot of negative, positive exponents. So the more that you practice this, the better. For these exponent questions, if you were doing it in a standardized test, maybe IBAP, they may recommend that you don't use a calculator for this. Now, of course, you can always take the mantissa and multiply them together, and then take the exponents and multiply these together. Of course, we just add 10 to the negative 17 squared and 10 to the 9. Likewise, you can do that at the bottom, and you'll get 180 squared, and then 10 to the negative 9 squared, which is 10 to the negative 18. That's going to throw out the figure. You should get the figure 7.1 by 10 to the negative 11 newtons. It is newtons, of course, because we're talking about one of the forces, the fundamental forces of the universe. So we would measure that in terms of newtons. And that is the force experienced by each charge. And that would be, to get the direction, you would look at the vectors above here and here, because it's a repulsive charge. Okay, so just to leave you with a more challenging example, a 6.0 microcoulombs, that is microcoulombs, or 10 to the negative 6 coulombs charge, is placed at the origin, and a negative 3.0 microcoulombs charge is placed 2 meters to the right. A third negative 8 microcoulombs charge is placed on the y-axis 2 meters above the first charge. So that third one is placed 2 meters above the first charge. What is the force on the second charge as a result of the other two? So again, very good idea to draw this scenario out. We're looking for the force on the second charge. I would recommend drawing an x and y axis in that instance. And of course, we know various things like this is 2 meters. And we also know that we've got a distance of 2 meters here. Now, one little tip that I'll give you is that you have two charges acting on Q2, two forces acting on Q2 rather. It is important that you solve each force, and then you're going to add the respective forces together. So bear in mind that very often this is a two-dimensional problem. You're dealing with vectors, and you've been given the tools to add two-dimensional vectors before. So good luck with that problem, and we will talk tomorrow in class.